All right, welcome everybody. Today we're going to continue with lesson number 51 about harmonic motion and trig graph applications, and we're going to pick up right where we left off in part A. As a reminder, when we're talking about simple harmonic motion, you're only going to be considering changes to A, B, and then potentially any negative. So we went ahead and did the first page together. So if you need to go back and review those simple direct applications of harmonic motion, feel free to do so. We're actually going to go ahead and do some of the more challenging ones on the back, but just a quick little reminder, I copied this from the first page since I had already written all over it. As a reminder, when you're talking about simple harmonic motion, again, you're talking about some distance or displacement d from the origin at the time t, and it's given by one of the following. It's either given by d equals a sine of wt or d equals a times the cosine of wt. And again, you'll know which is which depending on where the graph starts. If the graph or word problem starts at 0, 0, that's how you know that you're going to be using a sine. If you're talking about any other value, 0, any other number, that's how you know that it's a cosine. Then a couple of other things to remember. So the amplitude is always going to be the absolute value of A. The period, 2 pi over W. Remember, that's similar to 2 pi over B, but W just happens to be the value that they use in this case. And then frequency. So frequency you can think of in two ways. One is it's the reciprocal of the period. So if you want to think of it as being the reciprocal of the period, you're going to think of it as W over 2 pi. The second way for you to think about it is it's equal to 1 over the period. And again, you're going to use the definition that makes the most sense in the problem. So far on the front page, we've seen applications of both. So also from the front, remember that you're not just using harmonic motion for things that simply go up and down like a spring. You're talking about anything that rotates, oscillates, or makes some kind of a wave motion. So in terms of a wave motion, we're going to talk about a buoy in the ocean. So it turns out that it follows a simple harmonic motion pattern as the waves go by. It should be noted that the buoy moves a total of 3.5 total feet from its lowest point to its highest point, and that is denoted here by 3.5. So all the way from the lowest point to the highest point. Then it is important to note that it returns to its highest point every 10 seconds. Write an equation that describes the motion of the buoy if its highest point is at t equals 0. So if its highest point is at t equals 0, that tells us that this has to be a cosine problem. The only way that it could be a sine problem, remember, is if it starts at 0, 0. But if it's starting at its highest point, that means it has to be a cosine wave that then goes down and then comes back up. So now that we know that it's a cosine wave, a couple of other things that we have to figure out. So we know that we're going to be using the equation d equals a times the cosine of wt. We want to be a little bit careful for a. So 3.5 is the total distance that is covered during one of these motions. So the amplitude is only half that. Remember, the amplitude is the distance from the midline up or the midline down. So that means that if 3.5 is the total, each of these values would have to be 1.75. So the absolute value of A is equal to the absolute value of 175. So 1.75 would be your A. Then, because of the fact that they tell you that it returns to its highest point every 10 seconds, what they are telling you is the period is equal to 10 seconds. You're then going to use that to solve for W. So 10 equals 2 pi over W. Again, very similar to 2 pi over B, just a different variable. So 10W equals 2 pi. W equals 2 pi over 10, which would be equal to pi over 5. Turns out that's everything you need. So the distance is equal to 1.75 times the cosine of pi over 5 times t. Again, they do call it simple harmonic motion for a reason. It should be relatively simple, which hopefully you would agree. Let's look at number 8. So number 8, you're talking about a fishing bobber. That means when you fish, you attach it to the end of your line, you throw it into the water so that you can see where your line is. And basically it oscillates in simple harmonic motion from the waves while you fish. Your bobber moves a total of 1.5 inches from its highest point to its lowest point, and it returns to its high point every 3 seconds. Write an equation modeling this motion if your bobber is at its high point at time equals 0. So in this case, again, time equals 0 being your high point. That is how, again, we know that it's a cosine wave. Then a couple of additional pieces of information. So again, we're looking for D equals A times the cosine of WT. Because it's 1.5 inches in total, remember that your amplitude would have to be the absolute value of half that. So that would be 0.75. If it returns to its high point every 3 seconds, that's the period. So you're going to set that equal to 2 pi over W. So 3W equals 2 pi, which means W equals 2 pi over 3. So you can safely assume that D is equal to 0.75 times the cosine of 2 pi over 3t. Now, when it comes to problems that are not so simple, there is more work to be done, and there are limitations to how hard the problems are that I would ask you to actually find the equation from scratch. So an example of something that I would not ask you to find the equation from scratch, but just ask you to use it would be something like number 9. And notice that for the remaining questions, I'm calling this other applications of trig functions. So that means these are not following the simple harmonic motion formula necessarily. They might not, but we might have to add a little bit more to it. So circadian rhythms, maybe you've heard about that. That's in terms of people's body temperature and how well they sleep. And it also has to do with your blood pressure. So an individual's resting diastolic blood pressure at any given time t is given by the following. So B of t is equal to 80 plus 7 times the sine of pi over 12t, where t is measured in hours since midnight. And then the blood pressure is measured in millimeters of mercury. You're going to want to find this person's diastolic blood pressure at the following hours. So you don't know anything about blood pressure, or you don't know enough about blood pressure, I would say, to be able to create this equation. So if I wanted you to do something, I would have to give it to you. So here it is. Then I could ask you to find these calculations, and really the only thing you would have to do is make sure that you know what value of time to plug in. The important thing here being that T is measured in hours since midnight. So if you're talking about somebody's blood pressure at 6 a.m., that is 6 hours past midnight. If you're talking about their blood pressure at 10:30 a.m., that's 10 and a half hours past midnight. Noon would be 12 hours past midnight. And then 8 p.m. would be 20 hours past midnight. So I would expect you to be able to figure out what values of time would have to go into this equation. And then the truth is, you could use a calculator, and in fact, you should use a calculator to do these. I just want to make sure you understand that if you're going to be using a calculator, you do, again, have to be in radian mode because you're plugging in pi's. So when it comes to plugging them in, let's just go ahead and do the first one all the way through. So if we're talking about A, we're talking about B of 6, which again is the person's blood pressure at 6 a.m. or 6 hours past midnight. So 80 plus 7 times the sine, and basically you're going to plug a 6 in for t. So that would be 6 pi over 12. And again, you could and you should simply use your calculator. So if you have a calculator handy, take it out. Make sure that you're in radian mode. If you very carefully plug it in, we could do it without a calculator for some values, but it won't work for all of them. If we were going to do it without a calculator, 6 pi over 12, that reduces to pi over 2. Pi over 2 has a sign of 1. 1 times 7 is 7, and 7 plus 80 is 87. So the answer to A is 87. And again, for a problem like this, whether you did it with or without a calculator, it would not matter. And then to be honest, all the rest are the same thing. You're going to use a calculator. And just to confirm, if you want to go back later to see if you can do it right. So if you plug in 10.5, 12, and 20, you're going to get a blood pressure reading of 82.7, 80, and 73.9, respectively. So again, these are all calculators as long as you're in radian mode. So feel free to go back and try those at any time. Then let's talk about music. And again, you might have to know a little something about music for this to make the most sense. I'm going to try to give you what little information I do know. I'm not really a musician. So a tuba player is playing the E note and it sustains the sound for some time. For a pure E note, the variation in pressure is given by the following. So V of T equals 0.2 times the sine of 80 pi times T. Now, again, I don't know anything about music. I don't know how much you guys know about music, but you certainly wouldn't know enough to create that equation from scratch. So I could certainly, though, give you that equation and then ask you to do some stuff with it. So in part A here, it asks you for a couple of things. It asks you for the amplitude, the period, and the frequency. So the amplitude, hopefully you remember that the amplitude in this equation is simply going to be the number out front. So the amplitude has a value of 0.2. Then for the period, in order to find the period, you are going to do 2 pi over W, or 2 pi over B, which in this case would be 80 pi. So 2 pi over 80 pi means you have a period of 1 over 40, and in this case, it's seconds. Then, if you're being asked to find the frequency, hopefully you remember that the frequency, you can just take the reciprocal of the period. So the frequency is going to be 40. And again, if you want to say a little more, it's 40 cycles per, and we know that in this case it's seconds. On the previous side, we only knew generally time, but here we know for sure that it's seconds because they told us that we're in seconds. So those are all answers for A. Then to sketch this function might seem hard because you have relatively strange values, but you're actually going to do it the same exact way that you would have done it back in the, yesterday. So you might need a little bit of extra room, but if we're going to go ahead and sketch this, here's the information that we have. So we know that the amplitude of this function is 0.2. We know that the period is 1 over 40, and there's no other changes, there's no reflections, and there's no D. So you're going to graph this, again, using the 5 key points. So starting at 0, your period is going to be where you end, with is 1 over 40. Then you would take half that, and remember, if you're taking half of 1 over 40, another way of taking half is doubling the denominator, so that would be 1 over 80. Which would make this 1 over double the denominator, 1 over 160. And then if you're counting in 1 over 160s, then 2 over 160, then 3 over 160, and then 4 over 160, which again reduces. And then when it comes to the amplitude, the highest it can go is 0.2. The lowest it can go is negative 0.2. The sine wave goes from 0 to the maximum, back to 0 to the minimum, and then back to 0. So even if it's a word problem, even if the numbers are not that nice, you can still use all the graphing rules the same exact way. Remember, always and forever, you are going to focus on the 5 key points. Then going back, they ask you if the tuba player increases the loudness of the note, how does that change the equation? And then if they're flat, how does that change the equation? Now, the truth is, I actually had to look that up because, again, I don't really know enough about music. So I wouldn't ask you this like on a test, but just in case you're curious, if you're increasing the loudness of the note, it turns out that the amplitude increases. Whereas if you have a flat note, you're talking about a change in frequency and it's going to decrease. So again, I'm not going to ask you on a test or quiz to tell me about things about the world that you may or may not know, but it's just kind of a fun fact, which maybe you're interested in. And then finally, something that hopefully you can all relate to, you're talking about a point on the tip of a windmill. So again, because the windmill is going around and around and around, that's why it can be modeled with trig functions. So the x-axis represents time and the y-axis represents feet above the ground. So all important information that we are going to want to consider. When it asks you for the period of this function and what does it mean in context, so again, the period is the length of time it takes to go through one full cycle. Still, for now, we only know how to start at 0. So if you're going to go ahead and find one full cycle, then you're going to go ahead and look at this upside down cosine right here. And if you're going to go ahead and look at this, then you're going to conclude that the period equals 3 minutes. What does that actually mean? Well, this is the time for the windmill to turn around once. So again, it's a pretty slow moving windmill. It takes a full 3 minutes to go through the entire motion. I want you to envision how this is possibly happening. So I want you to envision a windmill. And I want you to envision the fact that it's going to turn in a circle. So you don't have to draw a windmill. You can just draw a circle. The fact that it is starting here at 0, 0, that means that you're assuming you're starting here on the ground at a value of 0. The fact that the highest value, which we can't see 100%, but let's say we were using a reasonable estimation. Let's say we reasonably estimate that to be 175. That would mean that the maximum is 175. So what do the Y values tell you about the windmill? So we're going to say, again, we're going to estimate that the height is approximately 175 meters. And that's what we can ascertain. Again, the lowest is 0 and the highest is 175. Then here's something else. If you take a look at the entire height of this graph, remember that the D would be halfway and your A would be the distance from the midline up or the midline down. So in terms of the midline, which would be your D, that would have to be half of 175, which would be 87.5. Again, it's not actually asking me for the equation, but it might in the future. So that's why I think it's good to talk about it. And then again, the amplitude is the distance from the midline up or from the midline down. And in this case, the amplitude would actually also be 87.5. Doesn't have to be the same, but in this case it is. And again, I could ask you for the equation. I could ask you for lots of things, but all I really want you to be able to do is recognize, 1, that the period is 3 minutes. 2, be able to give a reasonable estimate for the height, so 175. And then 3rd, again, because of the fact that you're starting down here at 0, 0, that means you're starting at the bottom of the windmill. That means that 175 would have to be all the way at the top. And the graph could change if you started somewhere else on the windmill. So if you started here when the windmill had already turned, you would be starting here on the graph. If you started at any other location, you would have to be starting at some other point. And just to give you a clue, that is the next thing we're going to talk about. And that is called a phase shift. And that's a change to letter C in our equation. And that's going to be the next thing. So that finishes lesson 51. You guys are now good to do homework 51. So thanks very much for tuning in, and we will catch you next time.